on that case here P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma, that is nothing but equal to constant, and this is nothing but equal to PV to the power of gamma. So what is here the pressure? So that pressure P is equal to C by V to the power of gamma. Substitute over here. Integral 1 to 2 constant, bringing all the volume terms dV by V to the power of gamma. V to the power of gamma. Right? So the integral of x to the power of n formula, that is x to the power of n plus 1 by n plus 1. Strong mathematics is also applied, that is either the differentiation or the integration you have to apply here. So on to this particular point where it is written as integral of 1 to 2 constant take out. So this is v to the power of minus gamma dv. Now you differentiate this one. So you will get as this c, and this is v to the power of minus gamma plus 1 divided by 2. Divide by minus gamma plus 1. The limits are 1 to 2. So what you will get here? C into V2 to the power of minus gamma plus 1 minus V1 to the power of minus gamma plus 1 divided by minus gamma plus 1. Minus gamma plus 1. But what about this C? See, here there is a volume V2 is there. So I will write that volume that is as in this way, that is P2 V2 and V2 to the power of minus gamma plus 1 minus, again here it is the P1 V1 and V1 to the power of minus gamma plus 1 divided by minus gamma plus 1. So this is cancelling, that is right, minus this is also here gamma, this is also gamma because it is this one p1 v1 to the power of gamma. So this is getting cancelling and this is also getting cancelling. So finally you could able to get p2 v2 minus p1 v1 divided by minus gamma plus 1, right? When you arrange the terms, you will get it as p1 v1 minus p2 v2 by gamma minus 1, right? So here it is the P2 V2 minus, so when we solve this particular expression, so when you solve this particular expression, finally you will get the work transfer relation as P1 V1 minus P2 V2 by gamma minus 1. So that is here you will get as a P2 V2 minus P1 V1 by minus gamma plus 1. Then you can write this one as P1 V1 minus P2 V2 divided by gamma minus 1. So this is the work transfer relation, right? So that when you apply the first law of thermodynamics, Q is equal to delta U plus W, delta U plus W, because this is 0, this is 0, then delta U is nothing but equal to minus W. Delta U is nothing but equal to minus W, right? So what is this one here? P1 V1 is nothing but equal to This you can write it as mr T1 minus T2 divided by gamma minus 1. mr T1 minus T2 divided by gamma minus 1. Right? What is this CV? CV is nothing but equal to R by gamma minus 1. CV is equal to C here. R by gamma minus 1. So you will get that is nothing but equal to MCV T1 minus T2. MCV. So that is this is nothing but equal to MCV. Actually, it is T2 minus T1. Minus sign is there. So when you remove the minus sign, you will get as T1 minus T2. So this is nothing but an isothermal relation. Sorry, this is nothing but adiabatic process. So how the heat transfer and work transfer relations for the adiabatic process? This is what you need to apply for solving the or developing the expression for work transfer for a adiabatic process. Work transfer for a adiabatic process. See here, PV to the power of gamma. PV to the power of gamma is there. So this PV to the power of gamma is there, right? So this is what all the work output you can get it. This is all the work output. The area under the PV plane is going to get out as the work output. Area under the PV plane. So that is area under the PV plane. You will get the work output from the system, right? Next one is the polytropic process. So the next point it is polytropic process. So in a polytropic process, see here, when a system changes from state 1 to the state 2 in a constant volume expansion, this is the expansion where the pressure is going to reduce. This is also the expansion P1 to P2. That is n is equal to 0. It is the isobaric process. See here, n is equal to 0, isobaric process. When n is equal to 1, that means the PV is equal to constant. N is equal to 1, PV is equal to constant, or isothermal process, or isothermal process, or PV is equal to constant. Next one is a polytropic process. So this is the polytropic process. Next, the isentropic process also you can represent like this one. That is the n is equal to gamma, and this gamma is nothing but equal to 1.4. Generally, for the polytropic process, n is equal to 1.3. For a polytropic process, this is how the curves are there. Now, W1 to 2. So that is after solving the equation. So here also what you need to represent is that is P1 V1 to the power of n is equal to P2 V2 to the power of n. Polytropic process is equal to constant. This is nothing but equal to PV to the power of n. So W1 to 2 is equal to integral of 1 to 2 P dV work. What is this P? P is nothing but equal to C by V to the power of n, right? So when you substitute this P, when you substitute this P as this one, right? Carry out that particular work, then you will get the equation as like this one: P1 V1 minus P2 V2 divided by n minus 1 by n minus 1. Then again you have to apply the heat transfer, that is Q is equal to delta U plus W. What is this delta U? Delta U is nothing but equal to MCV T2 minus T1 plus, in terms of the temperatures also I am going to apply in terms of the temperature, that is mr T1 minus T2 divided by n minus 1 divided by n minus 1, right? So here there is a r term is there, right? So I need to bring here also, that is m Cv is nothing but equal to r by gamma minus 1 into T2 minus T1 plus mr T1 minus T2 divided by n minus 1, right? So keeping this one, that is mr at the outside, right? So here T2 minus T1 is there. So let me write this one as initially, that is T1 minus T2 divided by n minus 1, and here we are also going to write it as T1 minus T2 divided by gamma minus 1, right? So that is now mr T1 minus T2 common, then 1 by n minus 1 by 1 by gamma minus 1. Then what you are going to get? Gamma. So here I can get it as gamma minus 1, gamma minus n divided by gamma minus 1. So gamma minus n divided by gamma minus 1 into polytropic work done. So what is this? This is the polytropic work done. So this is how the relations you can get it. And here also you need to substitute. What is this R? That R is nothing but equal to, CV. Sorry, that R is nothing but equal to, in terms of this relation, that is the CV is equal to R by gamma minus 1, r by gamma minus 1, right? Or in another words, where after writing this gamma minus 1, then you will get the n minus 1 as the polytropic work done, right? So try to be careful about this particular case. So here that is equal to mr T1 minus T2 gamma minus n, that is minus 1 and plus 1, it is getting cancelling, by gamma minus 1 into n minus 1. So I will take out this one, that is gamma minus n by gamma minus 1 into work done, right? So that is this mr T1 minus T2, and here cancel this one, but here you write this here. Then the total term you are going to be getting as, this is nothing but equal to W. So W into gamma minus n by gamma minus 1. So this is how you need to derive the expression for the polytropic process, that is work done in a polytropic process, and heat transfer in a polytropic process. So all these particular equations, so that we can get it. Heat transfer relations. So this I hope this completes all the reversible thermodynamic process. Reversible thermodynamic process means isobaric process, isochoric process, isothermal process, polytropic process, and adiabatic process. Next, there are two irreversible processes are there. That is, one is the free expansion process and another one is the throttling process. Two irreversible process. So the two irreversible process, the irreversible process will be represented on to the PV plane as in terms of dotted line, whereas the continuous process, that is the reversible process, are represented as a continuous line. So that is 1 to 2, right? So here free expansion, expansion of the gas against the vacuum, expansion of the gas. That means here there is a one partition is there. This is the partition, right? So it is a very light thin partition. So all of a sudden, if this gets punctured, then what happens? The gas is going to be expanded, and this gas is going to occupy the entire thing. But whenever the expansion is getting, you will get some work output. But here the work output is zero. Here the work output is zero. That's what this is the expansion of a gas against the vacuum. But there is no work output from this case. No work output from this particular. So the work is zero. When it is an insulated tank, if it is an insulated one, then if you apply the Q is equal to delta U plus W, the work transfer is zero and insulated one is zero. So finally only that is the which is going to get it is nothing but equal to the internal energy, right? So it is expansion of a gas, as the name implies, refers to the unrestrained expansion of the gas, unrestrained expansion of the gas. So let us take an insulated this one insulated tank having two compartments separated by a partition A and partition B, and assume that the compartment A is filled with gas while the B is having vacuum. If now the partition is removed, or if the partition gets punctured, the gas is allowed to occupy the entire volume. The gas is going to occupy the entire volume, right? So once this gas is going to occupy the entire volume, new pressure of the gas will be lesser. That is the new pressure is less than the initial pressure, right? So the expansion of a gas due to the removal of partition is nothing but it is the unresisted expansion due to the expansion of a gas in a vacuum. So this is known as the free expansion, and in a free expansion process, the work is zero and the heat transfer is zero. So that's why it is a irreversible process. That's why it is a irreversible process, right? And the throttling process, that is also the irreversible process, where you need to represent in terms of the dotted line. So only there are two processes are there in this side. Next one is the moving boundary work. So try to get the clarity onto the moving boundary work and non-moving boundary work. So before going to conclude that particular things, student has to get the meaning of this one, moving boundary work. See here, some gas is stored. Some gas is stored. When you give the heat input, when you give the heat input, the gas gets heated up. When the gas gets heated up, the gas is going to expand. When the gas expands, the piston is going to move up. So the work associated with a moving boundary is called the boundary work. The work associated with a moving boundary is called the boundary work. So one form of a mechanical work frequently encountered in practice associated with the expansion. Say sometimes the gas is going to be getting contracted. That means it is compressed. In that case, the piston is going to move down. Piston is going to move down. So therefore the expansion or the compression work is often called the moving boundary work, or it is simply the boundary work, right? And it is going to be involving the PDB work. So the moving boundary work is the primary form of a work involved in automobile engines. Moving boundary work is the primary form of a work in automobile engines. So all the automobile engines are connected with the moving boundary work. So during their expansion, the combustion of a gases are going to combustion. See here, the combustion of a gases is going to move the piston upwards. Very high pressure is created in this side. So force the piston to move, which in turn forces the crankshaft to rotate. The moving boundary work associated with the real engines, moving boundary work associated with the real engines are compressors. This cannot be determined exactly from a thermodynamic analysis. Thermodynamic analysis alone, you cannot get the work because the piston usually moves at very high speed and making it difficult for the gas inside to maintain the equilibrium. So this is what the student has to understand this particular studies. Now, when a system undergoes the different process, and the another thing what he has to understood that when a system changes from state 1 to the state 2 following the path A, in this case the work output is 10 kilojoules. When a system expanded from state 1 to the state 2 following the path B, the work output you will get it as 8 kilojoules. If a system expands the system 1 to the system 2 following the path C, you will get the work output as 5 kilojoules. Here what my intention is that what is the work output you can get in a constant pressure process, in a constant volume process, in a isothermal process, in a polytropic process for the same input condition. Say suppose if you give the same heat input, what is the conversion of the possible work output in a constant pressure process, constant volume process, adiabatic process, polytropic process. So that is the intention of this particular diagram sketch on a PV plane. So the boundary work done during the process depends on the path followed as well as the end states. Path followed as well as the, so for the same end state following the different path, then what about the work output, right? So that is now here there is the net work done during the cycle. This is the net work done. This is the net work done during a cycle is the difference between the work done by the system, right? So that is W net is nothing but equal to W 1 to 2 W net. That is here what is the work input minus what is the work output. Cycle is the difference between work done by the system, that is work output, minus work done on the system, what is work input. So this is the net work output from the cycle, right? So here there is a question is that what is that highlighted yellow color highlighted question. So that an ideal gas at a given state, an ideal gas at a given state expands to the final volume at constant pressure, and then at constant temperature, for which case the work done is greater. For which case the work done is greater. That is what he has to analyze. So the area under the PV curve, the area under the PV plane is going to give the work output. The area under the process, the area under the process, thus it is nothing but the boundary work which is greater in constant pressure case, which is greater in constant pressure case. How you will represent that one? So here this is the PV plane, this is the PV plane, and this is the constant pressure expansion 1 to 2, and this is the constant volume expansion, that is 1 to 2, right? And this is the isothermal process, that is the PV is equal to constant. So here P is equal to constant, here volume is equal to constant. Next one is polytropic process, PV to the power of n is equal to constant. Next one is isentropic process, that is PV to the power of gamma is equal to constant. Then your job is that now the area involvement. So in a constant pressure process, see, observe this one. This is the work output. This is the work output, right? So that's why it is greater in the constant pressure case. So this the area involvement in a constant pressure process is more. So you will get the more work output. That is the student has to understand into this particular content. So which process is going to give the more work output under the same initial and final state condition. Under the same initial and final state condition. The next one is, can a steady state device have the boundary work? Can a steady state have the boundary work? Means answer is no. Why? Any change in the size of the control volume. Steady state means control volume technique. Any change in the size of a control volume would neither require a change in mass inside or a change in state inside, and neither of which is possible in a steady state process. So that's why a steady state device have no boundary work. Have no boundary work. So there are some practical examples you can observe from this particular slide. A 300 watt refrigerator, which is equivalent to 300 watt resistance heater, 300 watt fan, and 300 watt TV. Two people such dissipating 150 watts of each, three light bulbs 100 watts each, and 100 watt computer with a 200 watt monitor, solar energy. So here the intention is that how much amount of heat it could be converted to the work. So if you are giving the 10 watts of a heat, out of that 10 watts, then how much work conversion of a possible form of a one form of a work, one form of energy to the another form. Say suppose if it, according to the first law of a thermodynamics, when you are giving 10 watts heat input, you are going to get the 10 watts work output, but it is not possible. But when you give the 10 watts of a work output, work input, you can get 10 watts of a heat output, right? So there are certain limitations are there. That limitations will be covered in the next unit, right? So that particular things you have to observe. So this is all about the first law of a thermodynamics, right? Hope today I have covered the energy balance equation for a closed system, and that energy balance will be the same for any kind of a process, that all you should have to observe. And the second one is the work transfer relations and heat transfer relations for various process in a closed system. Work transfer calculation and heat transfer calculation for various process when a system experiences energy interaction with the surroundings, right? So that particular derivations are covered. And in a irreversible process, there is a free expansion throttling process are there, so that it could be mentioned in terms of the dotted line. So dotted line. That is all about the today's class. Hope you have enjoyed this particular class. Thank you.